All right. So the probability concepts that we have discussed are by no means trivial things. They are things which are used in amazing, aspects. For example, we have Angelina Jolie, who happens to be an actor, and just because doctors predicted with some probability that she might get breast cancer, she has you know proceeded further and got her double mastectomy done. Mastectomy means removal of the organ. Just because people have predicted she did not have a trace of cancer when she has undergone the complete body check and all the tests, which all the tests have actually proved that she did not have even a trace of cancer. But despite that, just based on the probability values, she has got her double mastectomy done. And a lot of people hailed and told that, yeah, that's very heroic. Right? A lot of celebrities are doing that. A lot of affluent people are doing that. Based on the probabilities, they are taking decisions just to ensure that they remove the risk of they encountering cancer. Okay. Also, there is another use case. This use case is there in BBC, British Broadcasting Corporation, right? Even this use case happens to be there in BBC. Here, rather than talk about Amanda Knox, I would talk about Lucia de Burgh. She was a Dutch nurse, Netherlands, Holland. And under her supervision, a lot of kids died. And people thought she was killing the kids, and they have put her um, behind the bars. When she was produced in the court, not just lawyers, everyone else, including the judge, were convinced that she has committed the murder, and they have put her behind bars. After 6 years, and she was sentenced to life. She was sentenced to life in prison. And then, because of her, okay, anyways, so I would cut short the story. And then there was a statistician who has come to her rescue. And that statistician has proven to the judges that there is 0.00001 probability that Lucia de Burgh was involved in murdering the kids. And based on those probability values, the case was relooked at and the judge acquitted her. She was released after 6 years in prison. Look at the power and strength of probability. Any high profile case that is handled nowadays has the backing of probability. They're looking at what is the probability that someone has committed a murder, committed a crime, so on and so forth. They are not, expanding this to entire, all the cases, but they are certainly using, they in a sense, judiciary is using it on high profile cases before they take a decision. So that is how powerful probability concepts are. And now let us talk about inferential statistics. While we have the complete population, let me talk about all the iPhone customers, for instance. iPhone 13 customers. And say you have some 140 million iPhone 13 customers across the globe. And say Tim Cook, who happens to be CEO of Apple, walks up to you and says that, I want you to perform a survey on iPhone 13 customers and help me understand what features they are happy about and what features they are unhappy about. And if you were to go after entire 140 million customers, Okay, if you were to go after the complete 140 million customers, then it would be extremely time consuming and it will be very costly affair. By the time you complete surveying all the 140 million customers, probably iPhone 18 or 19 would be in the market. Hence, what we do is we need to come up with a sampling frame. And defining a sampling frame is completely business oriented. And this step is optional. Sorry. Either you come up with a sampling frame or you simply ignore that, doesn't matter. But however, if you want to come up with a sampling frame, it is business oriented, meaning you need to take a decision, cautious decision. Maybe you might say that, do you know what? Out of all the 140 million customers, 80% of 140 million customers happen to be in US and UK. 80% of customers are in US and UK. If you feel so, then you might take a business decision. It is optional, by the way. You might take a business decision that I want to take a sampling frame rather than go after 140 million customers. I would choose US and UK alone because by doing that, I would be looking at 80% of customers. On this sampling frame, you apply a technique called as simple random sampling. Simple random sampling. Using this specific technique, you get a sample. Simple random sampling, or SRS, as it is famously called as, is the only technique on the planet which is bias free. It doesn't have any bias. Because you're just closing your eyes and you're randomly choosing certain customers. And what percentage of customers do you want to choose as a sample really depends on you. It could be 10%, 20%, 30%, whatever. Right? Depending on the time and money that you have at your disposal, and depending on the kind of compute which is available, meaning what kind of server you have, how much amount of RAM you have, how many processors do you have? Do you have GPU machines, graphical processing units, etc.? Depending on all those aspects, you decide on how much data you want to take as a sample. Say you take 10% of sampling frame. If you do not have a sampling frame, you then take 10% of the entire population. In the good old days, people always used to say that, you know what, if you have 30 data points in your sample, then that is good enough for you to proceed further with your analysis. Good starting point. But this was a thumb rule which people have arrived at a few decades ago, when we did not have compute available, but when we did not have proper computers, right? When we did not have sufficient RAM available, sufficient GPUs available. That is when people have come up with this generic thumb rule, which says that if you have 30 data points, it is good enough and it's a good starting point. But as and how the hardware and the semiconductor industry started, innovating, the processes became faster and faster. The amount of memory that we have today is humongous. The storage capacity has increased. Given all these things, the more the data, better it is. If you have more data, you can analyze better and the results would be very close to your population. That's a simple thumb rule that you need to bear in mind. More the data, better it is. But if you feel what is the minimum count that we need to proceed further with our analysis, then the answer is 30 data points. Okay. If you have 30 data points, that's good enough to get started. Say 10% of the customers who are in US and UK, you surveyed them and you figure out that the camera resolution and the screen resolution is amazing. People are loving it. But people are not liking the battery life, maybe. Who are the customers who are telling you? 10% of customers who happen to live in US and UK. Though you are surveying only 10% of the customers, when you ultimately make statements to Tim Cook, the CEO, who has asked you to perform this analysis to understand what features iPhone 13 customers are happy and what features they are unhappy about. And though you worked on only 10% of the customers of US and UK, you make a generic statement. You draw the inferences by working on the sample. Okay, you draw inferences and then make statements about population. You tell to Mr. Tim Cook that, you know what? Customers are happy about the camera resolution and the screen resolution, but customers are unhappy about the battery life. Though you're working on 10% of the customers in US and UK, you are making such statements about the complete population. Since you're drawing the inferences by working on a sample, and you're drawing inferences about the entire population, the statistics is called as inferential statistics. Okay, this is called as inferential statistics. And most often than not, you would never go after the complete population. Doesn't make sense. So we make use of the sampling technique. We take a sample out of the population, work on the sample, analyze the sample, and ultimately make statements about population. And that is called as inferential statistics. Alongside that, we also have something called as hypothesis testing. We will talk more about hypothesis testing at a later point of time, but this is also inferential statistics, part of inferential statistics. Within this, we have something called as parametric and non-parametric. As I've told you, I'll be introducing the terms and terminologies and later on get into the zone of explaining the concepts. Because when I explain the concepts, at least these terms will be slightly familiar. And this is one reason I request people to read the mind map on a daily basis, at least to get yourself familiarized with these terms and terminologies. Okay. Now, we are going to get into this specific concept. So we are done with probability. Okay. We are yet to get into probability distribution. Okay. We have inferential statistics also. So before talking about this measures of central tendency, I wish to go back and talk about probability distribution. Now, if I say we have daily sales of Apple iPads, and say we have data I want to play this part once again. So for that, I think to just discard. So we have data for day 1, day 2, day. You see that we have data from day 1 until 100. You have all those 100 days of data. And on one axis or on another column, you have the sales of iPad. Okay. Since we cannot show all of those in a single slide, we have put that animation. Okay. And now I'm sure it's clear that we have data of all the 100 days. Okay. And you have data pertaining to Apple iPad sales. That is specific story. This is a random variable because the number of iPads that you sell varies. It will not always be the same. It might be 0, it might be 4, so on and so forth. It varies. And say you have data pertaining to 100 days. Now, each of these is given a notation like this. This is X1, X2, X3, X4, X5, so on and so forth. And overall, this is given a notation, uppercase X or uppercase Y or uppercase A, B, whatever, uppercase. And the lower cases would be for each and every value of that random variable. So assume that within this column called as sale of iPad, you have unique values which happen to be 0, 1, 2, 3, or 4. Either people have sold 0 iPads, or 1 iPad, or 2 iPads, or 3 iPads, or 4 iPads. So that's the data that you have. And you have the probabilities corresponding to that. So probability of selling 0 iPads, how do you calculate? Once again, we go back to the probability formula, which is number of interested events divided by total number of events. So probability of selling 0 iPads happens to be number of interested events. You're interested in 0. You just count how many times 0 appears. 1, 2, right? So if you count for all the 100 days, probably you'll find that on 40 days, you sold nothing. That means you sold 0 iPads. But probability formula is divided by total number of events. In total, you have data for 100 days. So this gives rise to 0.4, and that is exactly what we have here. And if you look at probability of selling 1 iPad, probability of selling 1 iPad, how do you calculate this? The interested event happens to be 1. You count how many times 1 appears. Say 1 appeared 25 times. Out of total number of events, which happen to be 100, so 25 by 100 would give you 0.25, and that is what we have here. Probability of selling 2 iPads, probability of selling 3 iPads, and probability of selling 4 iPads is provided to you. 0.4 and 0.25, 0.2, so on and so forth. Okay, from the historical data, from the raw data, you could deduce this. And we also discussed that when you add the probabilities of all these events, of all these values, possible values, you would get 1. 0.4 plus 0.25 plus 0.2 plus 0.05 plus 0.1. When you add all of those, you get 1. And if you take the overall probability of 1, and if you start distributing that across all these possible values, then this is called as probability distribution. All you're doing is you're distributing the probabilities across. Either you represent the probabilities in a tabular format like this, which is called as probability distribution table, probability distribution table. Or you might also want to have the probabilities represented using a graphical representation. So if you look at this on x-axis, for this probability distribution on x-axis, you have the random variable, which is number of iPads sold, 0 or 1 or 2, etc. 0, 1, 2, 3, 4. And on y-axis, you have probabilities. Probability values range from 0 to 1. And if you observe here, for 0, you have 0.4. For 1, you have 0.25. Very well. And for 2, you have 0.2. Then for 3, you have 0.05, and for 4, you have 0.4. So you have the bars in that way. For any graph that we are going to look at henceforth, you will have to remember two things. What would be on x-axis and what would be on y-axis? That's very, very important. Okay. And from this table, you can do a lot of calculations. If I ask you, what is the probability of having a sale? What is the probability of doing a sale? By looking at this probability distribution table, can you calculate that? If I were to ask you, what is the probability of doing a sale? When do you say you sold something? You can say you sold something if you sell at least one. If you sell at least one iPad, you say that you have sold something. 1 or 2 or 3 or 4, right? 0 means you did not sell anything. Probability of doing a sale means selling at least one. And when you look at this, you get, if you add all of these, probability of selling 1 or 2 or 3 or 4, when you add these, you get 0.6. So that's the answer. By looking at this probability distribution table, if I were to ask you on what is the probability of selling at least 3 iPads? At least 3 means either you sell 3 or more than 3. So you get 0.05 and 0.1. When you add these two, you get 0.15. Probability of at least 3 means 3 or more than 3. And you have the probabilities pertaining to that. When you add them, you get 0.15. Okay, next. So now I'll go back to the mind map. Yes, we have discussed about probability, probability distribution, inferential statistics. Of course, this mind map will contain additional information for your consumption. So please read that. And we are on an ongoing basis, continuously going to add more and more information to the mind map. And eventually, this information and a few other descriptions, etc., about each of these would get into our ebook. So make best use of the resources which are made available. Okay, now let's get into CRISP MLQ phase 2. We are done with phase 1. We understood what are the various activities to be performed as part of business understanding, and what are the various things that we need to do as part of data understanding. Now, we are moving to phase 2. Within phase 2, as I've told you, we are going to first talk about exploratory data analysis or descriptive statistics. And then we will get into data cleansing and feature engineering, the other stuff. Within exploratory data analysis or descriptive statistics, we have 4 moments of business decision followed by graphical representation. We have first moment, second moment, third moment, and fourth moment. At each of these steps or at each of these stages, you calculate certain measures, okay, and you're going to draw inferences pertaining to that. So A, you do some calculations. B, you answer the questions on what if. What if you get a specific value? What does that mean? That means you need to draw inferences. And then we also have graphical representation. And within graphical representation, we are going to talk about univariate, bivariate, majorly these two, and also you have multivariate plots, but they do not usually make a lot of sense. Okay. So we're going to talk about univariate plots, bivariate plots, and multivariate plots. And if you want me to be specific, then once we get into graphical representation, I'll talk more about univariate plots and bivariate plots that we are going to spend time upon. Now let's get into the first moment business decision, which is also called as measures of central tendency. And we have 3 measures of central tendencies: mean, median, and mode. So here is first moment business decision. And when you calculate the first moment business decision on the population, it's called as population parameters. If you work on a sample, it's called as sample statistics. This is a riddle which I'm going to ask towards the end. Let's see how many of y'all will crack it. So mean formula happens to be this. Population parameters are always represented using Greek notations. Like in this case, mu. All you're doing is you're saying take the summation of all the variables. So if you say x of I, and if I say I equal to 1, it refers to the first value. When I say I equal to 2, it refers to the second value. When I say I equal to 3, it refers to the third value, so on and so forth. And uppercase N represents the population. Uppercase N represents the population. And when you look at your sample, and when you calculate mean for a sample, it is called a sample statistic. And this is represented using X bar. This is a summation symbol. You are going to add all the values and you are going to divide it with N, and you see a lowercase n, and that's for sample. Uppercase N is for population. Lowercase n is for sample. Now let's resort to a spreadsheet and let's do some simple calculation. And let us try to understand the calculation of mean. What are the disadvantages of mean? And how do we actually overcome that? So here is a spreadsheet. Let me call this as dataset A, and say we have 5 numbers. If we want to calculate the mean or average of these numbers, how do we do that? One simple Excel formula is average. When you say average of all of these numbers, you get 3. This is how you calculate. We are going to do all these things in Python as well, right? But let's look at the formula because we are going to build on top of that. You add all of these numbers. Say this is the population, so I'm taking them. Assume for now that these are the 5 numbers that you have on the planet. All right, so this is our population. You add all these values and you divide it by n. This data set is given a notation uppercase X, random variable. When you substitute I equal to 1 in this, you get x1, x1, x2, x3, x4, and x5. Always the lowercase notations are used for the values within a random variable, x1. Summation, so you have a plus. When you substitute I equal to 2, you get x2. Summation is plus. When you substitute I equal to 3, you get x3 plus. Plus because summation. When you substitute I equal to 4, you get x4 and then summation. When you substitute I equal to 5, you get x5. And you have only 5 numbers. So it will be I equal to 1 until 5. And then you divide it by the total count. You have 5 numbers. So you divide by 5. So simply put, you add all these numbers. 1 plus 2 plus 3 plus 4 plus 5. And you divide it by the total count, which happens to be 15 by 5. And you get 3. And is that what we have got? Yes. So this is a simple formula to calculate your mean. Now, what if I copy the entire data set? So I'm copying the entire data set. I'll call it as data set B. And what if I change only a single number? If I change a single number from 5 to 700, for example, only a single number, mind you. And now if I were to calculate average of all these numbers, you get 142. I could have as well, dragged it in this way, but then I want to confuse you all with all those things. So I again calculated. Okay. I mean, do you see something strange here? Just because one number is different, average or mean is moving to a different location altogether. From 3, it is now 142. There's such a huge difference. And the mean gets heavily influenced when you have these kind of values in your data set, which are extremely different than the remaining values. And these kind of values, which are extremely small or extremely large in comparison to the other values, would be called as outliers or extreme values. Okay, these would be called as outliers or extreme values. Hence, mean is not a good measure when you have outliers in your data set. What if I have huge number of data, millions of rows? How do I identify outliers? Do I need to eyeball the way we are manually looking at it and identifying outliers? Do I need to go through all the millions of records and then determine outliers? Not really. There is a different technique called as box plot to do that. We are going to talk about that later. But, say you're joining some B school. And that B school promotes that on an average, our students who get graduated to us will get, say, $300,000 per annum. You might be tempted. You might feel that $300,000 per annum. Wow, that sounds cool. And You might want to get admitted into that college. So you study very hard and get admitted. But the reality would be something else. People might get $60,000 per annum. A few people might get $80,000 per annum. Say another student also got $60,000 per annum. And there was one guy who got $1 million per annum as salary. Now, this $1 million per annum salary person would certainly be an outlier. This is such a huge number. Now, if you were to, let me take this and put somewhere else. Okay, this is what the B school is marketing as. And then if I take the average of the salaries of these folks, it is going to turn out to be $300,000. Okay, but ideally, the $300,000 is something which is coming up just because you have this outlier. So what is it that this B school is trying to do? They're trying to sidetrack your attention. They want you to focus on an average value, the mean value, as opposed to all the other values. When you look at the underlying data, you would come to know that, hey, majority of the students will get their salaries in the range of $60,000 to $80,000 per annum. Probably one of students might get $1 million, and I would use that number in the calculation to come up with average. And this is what I'm going to market to the outside world. I'm going to say that students who get graduated to us get $300,000 per annum on an average. There's nothing wrong with that. Okay, but now that we understand about outliers, we should be a little careful. Okay, and when you have outliers, median is a better measure. And what is median? Median is the middle value of datasets. The middle value of the datasets is called as median. What is the middle value here? It happens to be 3, so the median is 3. And one another thing is median does not get influenced by outliers. So even if you have an outlier here, what is the median going to be? The middle value, which is 3. So is median getting influenced by outliers? Not at all. Now let me take another data set. See. Okay. Now if I say 1, 2, 3, 4, 5, 6. And if I ask you to calculate the median, you don't have a single value which is an outlier, which is a middle value. You have both of these, which happen to be the middle values. Then which one should I select as a median? In this kind of a scenario, you take an average of these numbers, and then you get 7 by 2, which is 3.5. Or you might as well apply the formula of median in Excel. Median of this data set would be 3.5. And is that what we have got by doing a manual calculation? Yes. Let me now give you another data set. What if I say 3, 1, 700, 2, and 4? Now, if I were to ask you to calculate the median of this data set, what would that be? Median is the middle value. Would that be 700? Not really. We also discussed that median will not get influenced by outliers. Didn't we discuss? Yes, we discussed. Then if you take 700, that means median is also getting influenced by outliers. So what you need to do is first, you need to sort the data in a sequence. Once you sort the data in the sequence, then you're going to choose the middle value of that, and the middle value happens to be 3. Okay, this is how you calculate median. We'll just calculate mode as well. Whenever, okay, let me do one thing. Okay, anyways. Suppose you have another data set and you have customer satisfaction score as satisfied, dissatisfied, neutral, then say satisfied, satisfied, etc. Okay. So if you have this kind of a data set where you have categorical data and say you have customer satisfaction score, whether you're satisfied with your job or dissatisfied with your job, or are you neutral? Say you have this data. If you were to calculate mean of this data set, whenever you have categorical data, mean is not applicable. For that case, even median is not applicable when you have categorical data. So the only thing that makes sense is called as mode. Mode is that value which repeats maximum times. What is the value which repeats maximum times in this data set? Satisfied, it appears 3 times. So you have a mode called as satisfied. If you have a single mode, it is called as unimodal. Suppose you also have neutral. Now, how many modes do we have? Satisfied is appearing 3 times and neutral is also appearing 3 times. So satisfied as well as neutral would be the modes. You have 2 modes here. When you have 2 modes, it is called as bimodal. When you have 2 modes, it's called as bimodal. You can also have more than 2 modes, and when you have more than 2 modes, it is called as multimodal. And friends, we are going to talk about something else later. But remember one thing, that if you're, say, trying to plot salaries of people, income, and then if you get a distribution like this, data distributed like this, that means this could be salaries of all male or female employees, and this could be salaries of all the male employees. And you know what? In this kind of a setup, you'll have bimodal representation. The moment you have bimodal, one thing should come to your mind, that, hey, there might be presence of 2 different segments or 2 different clusters. What do you mean by clusters, segments, etc.? We'll talk about that later. For now, in this example, assume that you have income of all the female employees and you have income of all the male employees. Those 2 are getting represented as 2 segregate segments or clusters. You can have more than 2 also. Okay, you can have more than 2 modes, and having more than 2 modes would represent, would mean, or would imply that you have more segments or clusters. Okay, so mean and median can be calculated when you have numeric data. That is, when you have continuous data or count data. That is, when you have quantitative data, you can calculate mean or median. Mode can be calculated when you have count data as well. But when you have categorical data, you can calculate only mode, nothing else. Okay, so that's our median, which is the middlemost value of the data set, and you have mode, which is a value which repeats maximum times. Here is a riddle. Just try to ponder upon that and try to understand what's happening. I'll ask the question and I'm going to reveal the answer in the next module. Two head of data science departments, say, went on a hunting. And then they both see that a black panther is charging at them. And one data scientist releases an arrow, but that arrow misses the panther from the left side. Okay. And another data scientist also releases the arrow, but it misses the panther from the, one misses from the left side, another misses from the right side. But then both of these people would be partying and jumping with joy. What might be the reason? Just think through, and it is related to measures of central tendency. And why is it called as first moment business decision as well? Because these are the first set of questions which any management person would ask and should ask. For example, say you have your branches, say your bank head of HSBC. Okay, and say you're head of HSBC ASEAN market, HSBC Bank. And say you have your bank branches in Malaysia, say you have in Singapore. Of course, you have across, but then just for our example, say you also have your branch in Indonesia. As a head of ASEAN market, your first question should be and will be, on an average, what are our sales? On an average, what are our profits? On an average, how many employees work? On an average, what is the attrition rate? On an average, how many footfalls do we have? On an average, how many credit cards do we sell? On an average would be the very first question which any management person should ask and will ask, and hence measures of central tendency is also called as first moment business decision. These are a few things that you need to calculate. Okay. So I'll stop here, and in the next module, we shall talk about the solution to this riddle, and we will get into the other measures of or the other moments of business decision, that is second moment, third moment, fourth moment, etc. Here it is also called as first moment because in the formula it is whole raised to the power 1. Whole raised to the power 1. This is yet another reason on why it is called as first moment business decision.